So in this video, we're going to look at another solution concept called the mixed strategy Nash equilibrium. Mixed strategy Nash equilibrium is useful solution concept, especially where you cannot use the pure strategy Nash equilibrium concept to find the equilibrium of the game. So if you remember, we considered a game previously called the matching pennies game. In that game, we did not have a Nash equilibrium in the pure strategy. So this concept of mixed strategy Nash equilibrium will be helpful in finding equilibrium in the matching pennies game. Additionally, even if a game has pure strategy Nash equilibrium, we can always find a mixed strategy Nash equilibrium for that game. So let's look at the formal definition of mixed strategy Nash equilibrium. So consider a strategy profile sigma, where sigma is the mixed strategy. It's a probability basically we're looking at for every player who's playing the game. So we have mixed strategy for player 1, player 2, player 3, up to player n. So profile sigma is a mixed strategy Nash equilibrium if and only if the expected payoff for player I from playing the mixed strategy sigma I given other players' mixed strategy sigma sub minus I is at least as good as the expected payoff for player I once he plays a pure strategy Si prime given other players' mixed strategy sigma sub minus I. And this holds for each pure strategy Si prime belonging to the set of pure strategies for player I and for each player I. In other words, sigma I is a best response to sigma sub minus I for every player I. So in simple words, it means that the mixed strategy for player I is a best response for the other players, mixed strategy, sigma minus I. So they should match basically. That is the idea, right? Like we had previously in the pure strategy equilibrium. All right, so let's look at a game to understand. So let's not, I think I misspoke here. It's not about matching like we did in the pure strategy Nash equilibrium. Let's keep the definition to this. Sigma I is a best response to other players' mixed strategy. Okay, and this is true for every player I. All right, so let's consider a game. So let's write down the game here. So let's say it's a lobbying game. So I'm gonna draw it here. So the game is played between two firms. We can call them firm X and firm Y. And they have two strategies to play the game. Firm X can lobby to the government or not lobby to the government. And similarly, firm Y, it can lobby to the government and not lobby to the government. Okay. So each firm may lobby to the government in hopes of persuading the government to make a decision that is favorable to the firm. So the two firms X and Y independently and simultaneously decide whether to lobby L, right, or not lobby. So these are the two strategies, right, L and N. Lobbying entails a cost of 15. Okay, so think of dollar terms basically. So when the firms engage in lobbying, is going to cost them $15, and not lobbying costs nothing, $0. So if both firms lobby or neither firm lobbies, then the government takes a neutral decision, which yields 10 to both firms. Okay, so if neither firm lobbies, then the government takes a neutral decision and both firms will end up getting $10. Okay. A firm's payoff in this is this value minus the lobbying cost if it lobbied. So if firm Y lobbies and firm X does not lobby, then the government makes a decision that favors firm Y. That's the idea behind lobbying. And yielding 0 to firm X and 30 to firm Y. So therefore, firm Y's payoff in this case would be 30 minus the cost of lobbying. So 30 minus 15 is 15, all right? And if firm X lobbies and firm Y does not lobby, then the government makes a decision that favors firm X, yielding, let's say, $40 to firm X. So X's payoff in this case would be 40 minus 15. Okay, so 25, and 0 to the other firm, which is Y. So let's complete the normal form of this game. So the payoffs are -5 and -5 and 25 and 0 and 0 and 15. All right. So you can look at this game and you can verify here that there are two pure strategy Nash equilibria. So they are N and L and N. So this one and this one, right? These are the two pure strategy Nash equilibria in this game. So basically you're looking at, if firm Y lobbies, then the best response for firm X is to not lobby, right? 0 is better than -5. And if firm Y does not lobby, then the best response for firm X is to lobby. 25 is better than 10, right? And if firm X lobbies, then the best response for firm Y is to not lobby. So here they match best responses, and that's your Nash equilibrium in the pure strategy. And if firm X does not lobby, then the best response for firm Y is to lobby, right? 15 is better than 10. So here again, the best responses match. So that's your Nash equilibrium. So we have two Nash equilibria in this game in the pure strategy. But in addition to that, to these pure strategy Nash equilibria, there is also a mixed strategy Nash equilibrium, and to find it, recall that what must hold in a mixed strategy equilibrium is that a player must achieve a best response by selecting a mixed strategy. Okay, so here in this game, let's guess that firm X mixes between lobbying and not lobbying. Okay, if this strategy is optimal for firm X in response to the firm Y's strategy, then it must be that the expected payoff from playing L equals the expected payoff from playing N. Otherwise, firm X would strictly prefer to pick either L or N. So how can firm X's strategies, L and N, yield the same expected payoff? It must be that firm Y's behavior generates this expectation, because if firm Y played a pure strategy, then X would strictly prefer one of his strategies over the other. So let's suppose Q denotes the probability that firm Y plays L, and 1 minus Q would be the probability, therefore, that the firm Y plays N. So Q and 1 minus Q, these are the probabilities. So let's say firm Y plays L, lobbies, with a probability Q, and with a probability 1 minus Q, the firm Y does not lobby. Okay, so those are the probabilities. So these are the mixed strategies here for firm Y. So against this mixed strategy of firm Y, firm expects to earn, let's write down the expected payoff for firm X if firm X plays L, okay? So UX, so expected payoff of firm X, given firm X plays L, right? And we have other firm, which is Y, playing its mixed strategy, Q and 1 minus Q, right? So we'll just say sigma, which is the mixed strategy, right? Probabilities for firm Y. So if firm Y plays, lobby with a probability Q, then firm X will get -5 with a probability of Q. So 5 times Q, -5 times Q. Plus, if firm Y does not lobby with a probability of 1 minus Q and firm X chooses to lobby, then it gets 25 with a probability of 1 minus Q. So the expected payoff is equal to, you can simplify it. So -5Q plus 25 times 1. So then 25 minus 25, so 30Q. Okay, so 25 minus 30Q. All right, so that's the expected payoff from playing lobby for firm X. And if firm X chooses not to lobby, then the expected payoff for firm X would be, so firm X would get 0 with a probability of Q, so 0 times Q, plus it gets 10 with a probability of 1 minus Q. So this will simplify to 10 minus 10Q. Okay, so for firm X to be willing to randomize, it must be that the expected payoff from playing L is equal to the expected payoff from playing N. Okay, so you can set them equal. So 25 minus 30Q, the expected payoff from lobbying for firm X, should be equal to the expected payoff of not lobbying for firm X. So that would be 10 minus 10Q, right? So in this case, this will simplify it. You can solve for Q. Q is the only unknown here, right? So if you solve for it, Q would be equal to 3/4. So in other words, firm X can randomize in playing a best response if firm Y's strategy is 3/4 and 1/4. 1 minus Q is 1 minus 3/4 is 1/4. So 3/4 and 1/4. So if firm Y is going to choose, lobby and not lobby with these probabilities, then the, firm X has an incentive to randomize between its two pure strategies. Okay, so that's here. So next, let's look at what is firm-wise incentive, okay, in randomizing. So it's a similar exercise we're going to do now for firm Y. What we did is for firm X, right? So now we can assign probability of P. So let's use a different color here. So let's say firm X chooses to lobby with a probability P and not lobby with probability 1 minus P. Keep in mind the probabilities must add up to 1. So P plus 1 minus P is equal to 1. Okay, it's always, you always have to be careful about that. Okay, so now let's look at the expected payoff of firm, Y. So I'll move on to the next page here. Okay. So if firm Y selects L, its expected payoff is, so it will get, this. It's going to get -5 with a probability of P. And so let's write down fully. So you're looking at expected payoff for firm Y, given it selects to lobby and given the firm X's next strategy. Okay. So -5 times P plus 15 times 1 minus P. So this will simplify to 15 minus 20P. And similarly, if firm Y chooses not to lobby, so expected payoff for firm Y from not lobbying, given the mixed strategy of firm X, is equal to so it's equal to, you can just look at the payoffs here. So firm Y is choosing to not lobby, right? So it will get 15 if the firm X is okay, so that will be equal to, all right, so 10 minus 10P. Okay, so this would be this is the simplified one like this. All right, so next, so firm Y is indifferent between its two strategies, right? And therefore it's willing to randomize if this expected payoff is same as this, right? So we can set them equal. So 15 minus 20P is equal to 10 minus 10P. Okay, and which will so you have to solve for P now. So this will be P is equal to 1/2. P equals to 1/2. So 1 minus P is also equal to 1/2. So in this game, the mixed strategy profile 1/2, 1/2, and 3/4 and 1/4 is a mixed strategy Nash equilibrium. So given firm Y's mixed strategy, firm X's mixed strategy is a best response. And likewise, given firm X's strategy, firm Y's prescribed strategy is a best response, right? So keep in mind that while constructing a mixed strategy equilibrium, we look for a mixed strategy for one player that makes the other player indifferent between her pure strategies. And this is the best way to calculate mixed strategy equilibrium. All right. So Also, keep in mind that if the game has more dimensions, so we are just considering here 2x2 game right now. But if the game has more than 2 dimensions, let's say 3x3 game or 4x4 game or something like that, what you might want to do is first look for the dominated strategies in the game. And if the strategy is dominated, then the players would not assign any positive probabilities on those dominated strategies. So you can strike them off and reduce the game in size. So that way it would be manageable, and hopefully, you can bring it to the 2x2 game where you can calculate the mixed strategy in the fashion that I just described.